Welcome to lesson 1.6, Betweenness and Distance. So the idea of betweenness, what it means to be between something, has a little bit more specific of a definition in mathematics than it does in everyday life. For example, we could say the city of Milwaukee is in between Fond du Lac and Chicago. So we know it's generally somewhere in between, but it doesn't mean the exact same thing as in math. In math, in order to be between something, it needs to be on the same line or collinear. So a point is between two other points if it's on the same line and the coordinate is between their coordinates mathematically. So for example, if we have a at -2, b at 7.3, and u at 4, and they're all on the same line, u is between a and b. If u was up here, it is no longer between because it's not on the same line. Then a definition of a segment. Looking at the idea of betweenness and distance, segments have endpoints, so they can be measured. So they tie into this lesson quite a bit. So a segment is a set consisting of distinct endpoints and all the points in between. And we name it by the endpoints in any order. So if we look at this example here, this would be segment AB. So we could write it as segment AB or segment BA. It's the same exact thing. We name it by the endpoints in any order. Then we have the idea of a ray. A ray is a part of a line with one endpoint. It's named by the endpoint first and then any other point on that ray. So for example, looking at this, we have ray AB. I know that A is the endpoint because that's where it technically starts and it goes toward B forever. So when we name that, we have to put the endpoint first under the ray symbol. So the ray symbol is basically an arrow going to the right. So you always start with the endpoint. So this would be ray AB. Even if the ray is drawn going to the left, like this one, starting at A towards C forever, we still put the symbol going toward the right, and we start with the endpoint, so it'd be ray AC. And then our bottom example here, we have line BC. We could name this with any 2 points on the line in any order. So again, a reminder for a line, you can name it with any 2 points on the line in any order. So we could call this line CA, AC, BC, CB, AB, or BA. All of those would be that same line. And speaking of lines, lines are created by opposite rays. Opposite rays are 2 rays that share the endpoint, but they go in opposite directions. So for example, if I'm looking at this line here, ray AB and ray AC are opposite rays. So ray AB and AC share an endpoint of A, but they go in opposite directions. So opposite rays give us a line. So example 1, use the diagram to answer the following questions. Name 3 different ways to name that line. So we just need any 2 points on the line in any order. So we could call it AD, BC, CA, just a few. In B, 2 other names for ray AB. So ray AB, if we were writing it with the symbols, would be like this, with words like this. 2 other names mean we have to start at A and we're going toward B forever. So ray AC and ray AD would be the same ray as AB. And then another name for segment CD. So the symbol would be this, segment CD. With a segment, we name it by the endpoints in any order. So we could also name that segment DC. And then we're going back to those postulates and theorems that we talked about, and we're going to look at a distance postulate. So the distance postulate is broken into 3 parts. The first part is the uniqueness property. And the uniqueness property says on a coordinatized line, a number line, there is a unique distance between 2 points. So on a number line, if we have points A and B, there is only one unique distance for those 2 points. The distance formula states if 2 points on the same line have coordinates x and y, the distance between them is the absolute value of x minus y. And a reminder, absolute value means how far away from 0. It's these 2 vertical lines for the symbol. So that would always make our distance positive. You cannot have a negative distance in this case. And then the third part of the distance postulate is the additive property. The additive property simply states if B is on the segment AC, then AB plus BC equals AC. So if B is on the segment of AC and it's between them, then AB, the distance from A to B, plus BC equal the whole thing of AC. So in other words, the 2 parts make the total segment. So a couple examples of those. In example 2 here, they give us some information. They tell us E is between points G and F, so we know they're on the same line. The distance from G to E, 2 letters next to each other means the distance. So the distance from G to E is 9, and G to F is 27. What is the distance of E to F? So I just labeled my drawing. I know GF was 27, GE was 9, and we're looking for EF. So if I take the distance of GF minus the distance of GE, I would get the distance of EF. So 27 minus 9, 18 is the distance of E to F. Example 3, same idea with the segment addition postulate. So they gave us this information. AB was 6, AC was 17, and CD was 8. They want us to answer what is BC and what is AD. So again, to help me visualize it, I went in and labeled my diagram. AB was 6, A to C was 17, and C to D was 8. So the first thing I noticed to get BC is BC would be AC minus AB. So 17 minus 6 gave me BC of 11. Then AD, we could figure out 2 different ways. AD is the 3 parts, AB plus BC plus CD, or the 2 parts, AC plus CD. Either way we do that, we end up with the distance for AD being 25. Example 4. In example 4, it says in the figure below, the distance of G to E is x, E to F is 2x, and G to F is 42. What is x? What is EF? So in this case, we know G to F was 42, GE was x, and E to F was 2x. So I know x plus the 2x equals 42. So 3x equals 42, divide by 3, and x is 14. Then to figure out EF, we know EF was the expression 2 times x. So substitute the 14 for x, 2 times 14, and we know the distance from E to F was 28. And then our final example, is a word scenario with a range for possible answers. So what I mean by that is, let's first read through the scenario and then draw a diagram to make sense of it. So what we know is at a field day, the judges were stationed along the straight course of 100-meter. So we know it's a straight race. So it's a 100-meter segment. Judge A was 40 meters from the starting line. B was 10 meters from the finish. And Judge C was in between them, but he was at least, or she was at least 10 meters away from each of them. How far from the finish line was Judge C? So I simply drew myself a segment with endpoints of start and finish, and I knew that was 100 meters. Then I placed Judge A being 40 meters from the start. Judge B I placed 10 meters from the finish. And I know C is at least 10 meters away from both. So if I would go 10 more meters in from the finish, that would put me at 80 meters away from the start. And if I would go 10 meters away from the 40 meters that A is, that puts me at 50 meters from the start. So Judge C from the start could be anywhere in between 50 to 80 meters, and that would meet these requirements. But they're not asking how far from the start, they're asking how far from the finish line was Judge C. So I have to look at it in reverse. Judge C could be 20 meters away and then up to 50 meters away. So Judge C could be anywhere greater than or equal to 20 meters away from the finish and less than or equal to 50 meters from the finish line. So anywhere in this range of 20 meters to 50 meters would be an acceptable distance. So as you can see, a lot of what we're doing today comes back to definitions, that idea of understanding betweenness, segments, rays, and opposite rays, and then applying that to figure out distance by using the different parts of the distance postulate.